For Cliff Notes number 31, we're going to revisit the fundamental theorem of calculus. And it's right here for us. Graphically, this just means the signed area bound by some left x, some right x, a function, and the x-axis. To evaluate this integral, we need to find the antiderivative and evaluate it at the upper and lower limits. This integrand is ready for integration, so I'm not going to rewrite it. I'm just going to jump into the antiderivative. That's x to the fourth. The antiderivative for 6x would be to increase the exponent to 2 and divide by the new exponent. And we're going to evaluate from 1 to 2. So I'm going to do a little cleanup before I do the evaluation part. Alright, so plug in 2 everywhere you see x, so 2 to the fourth is 16, plus, plug in 2, squared is 4, 4 times 3 is 12. Evaluate at the lower limit, that's 1, so that's 1 plus 3. So we have 28 minus 4. So the answer is 24. For example 2, we're going to evaluate the integrand sine of x. Sine of x's antiderivative would be negative cosine. You could check by differentiating. The derivative of cosine is negative sine, so we would need another negative to make it a positive sine x here. So easy enough. You can leave the negative with the function cosine. I'm just going to go ahead and pull it out front. And as a final step, I'll just take the opposite of my answer. That way I can just evaluate the upper and lower limits at just cosine of x. So cosine of pi over 4 minus cosine of 0. And cosine of pi over 4 is square root of 2 over 2. Cosine of 0 is 1. You're finished. If you want to distribute the negative, that'd be fine. Oftentimes you'll see the negative distributed and then perhaps rearranged. Okay, if I distribute, the negative 1 over here becomes positive. Anything's acceptable. If it's multiple choice, you just have to look for the correct form. For example 3, we're going to get to revisit the e to the u integration rule. All right, so u substitution. U will be the exponent. I'm going to have to bring in a negative 4 and pull out a negative 1/4. So I'll do it right here where there's a little more room. So I'll have e to the negative 4x, and then I'll have the negative 4 right here. Okay, so this gets replaced with u. This will be replaced with du. Okay, and once it looks like this, it's in this exact form, we can integrate back to e to the u. Negative 1/4 ready to integrate. E to the negative 4x evaluated at 0 to 1. So e to the negative 4, e to the 0. And we know that's going to be 1. You're finished here, but there's various forms of this answer. You could pull the negative 4 down with the e to the denominator and create a fraction here. You can distribute the negative 1/4. A lot of different choices. So I'm going to go ahead and distribute. and just write it in several different forms. Again, any of these are correct. If I'm doing a free response question, I would probably leave it just like this. Something else you could do here is you could get a common denominator. That would require you to multiply the 1/4 by e to the 4 over e to the 4. In doing so, you rewrite as a single fraction with the denominator of 4e to the 4th. Likely the numerator would be in the reverse order here. All these are fine. All right, taking a look at number 4. I'm going to notice that I can pull out the constant multiplier of 5, and I'll probably do that. I think what's interesting about this problem is the lower limit of natural log of 2. And when you're working with an exponential function with a base of e, likely things are going to cancel. So this question is probably more about the limits and how to handle them when you have a natural log and a natural exponential, because the integration of e to the x is simple. It's basic. It just goes back to itself. So 5 times the antiderivative here is just e to the x, okay, evaluated from natural log of 2 to 3. All right, and I probably will pull the 5 out again, make it less complicated. So now we can just focus on evaluating e to the x. So we're going to have e to the 3 minus e raised to the ln 2. There's a little cleanup you can do. So that would be e cubed minus, those two undo each other, oops, leaving 2. You can leave it factored out, or you can distribute the 5. Alright, studying number 5 and looking at the integrand, just trying to get our plan together about how we're going to find an antiderivative. Oftentimes students will think, well, let's use u substitution and let's let u be x squared. And that's certainly a great option to begin with, but think about that for a minute. Project ahead a step. If u is x squared, then the derivative is 2x. And while I can bring in a 2 multiplier, I can't bring in a minus 4 here, an addition or a subtraction of a constant. So u substitution with u being x squared isn't going to work. And this is one integrand where you just have to remember to separate, to break apart. I like that technique. However, a lot of you guys might want to bring up x squared as x to the negative 2. That's certainly fine. When you bring up x to the negative 2, don't forget to distribute and then integrate. I'm going to go ahead and just do the break apart method. Okay, because I'm dividing by a monomial, one term, I can put x squared under x, and I can put x squared under 4. So I'm going to go ahead and do that. But I'm going to do it mentally. X over x squared is going to reduce to, if I were to break it apart, x over x squared is going to reduce to 1 over x. Minus, and then that's just 4 over x squared. Right, thinking about the integration rules that I know, I can term by term use different integration rules. 1 over x is going to go back to natural log. However, 4 over x squared is going to need to be integrated with the reverse power rule. So I'm going to go ahead and pull up x squared to x to the negative 2. So I'm not going to do any integration yet. I'm just going to get it ready for integration. I'll leave 1 over x. Until I'm ready to integrate all of my terms, I'll probably just rewrite the problem. So I'm just rewriting 1 over x here. It just kind of comes along for the ride. All right, ready to go? 1 over x integrates back to natural log of x, the absolute value of x, that is. Okay, for this term, we're going to increase the exponent. So I'm going to write down minus 4x, increase to negative 1, and divide by negative 1. Which we'll simplify in just a second. All right, before I plug in the limits, let me go ahead and do that. Okay, these two negatives will create a positive situation. And so that'll leave me with 4 over x. Okay, because if those both turn to positive, I'll go ahead and pull the x back down to the denominator because I prefer to work with exponents that aren't negative when I'm doing the evaluation part of the FTC. Okay, so we're ready to go here. Okay, so natural log of absolute value of 2. We can drop the absolute value signs because it's positive already. Plus 4 over 2, which is just 2. Plug in 1. Natural log of absolute value of 1 is just natural log of 1, which we know will be 0 in a second. And then plus 4 over 1, so just plus 4. Alright, so the brackets are no longer needed, so natural log of 2 plus 2. Alright, this is going to go to 0, so I just have minus 4. Alright, so natural log of 2 and then minus the 2. Alright, so for example 6, this one's going to seem a little strange because we haven't covered quite this idea yet. It's a very basic, simple idea. And so look at the choices here. It says using the substitution u equals 2x plus 1, this integral with x's can be expressed as one of the following 5 choices. Well, all 5 of the choices have u left in the integral. Alright, so let's go ahead and proceed with u substitution and kind of see what happens. Okay, if u is told to me to be 2x plus 1, then I need to find du, which is 2 dx. So that tells me I need to bring in a 2 and pull out a 1/2. And so when you look at the choices here, you can see that d and e don't have that 1/2 multiplier, so they're out. Okay, so I'm going to kind of come down here. So far I have 1/2 integral 0 to, all of this will be u to the 1/2, or just simply, I guess we'll leave it as a radical u. So u is the inside function on that square root, and then all of this will be replaced with du. Okay, and so when you start to look at the choices, many of you guys are going to want to choose B. However, B is not the correct answer, because if you're going to stop here, this is a new kind of concept, if you're going to stop here with a u integral and integrate with u instead of x, then you have to come off of the x limits and change to u limits. So what that means is if you're going to stay with the u integrand, like all these choices are presented to you in, you've got to take the lower limit, 0, plug it in for x, because it's an x limit, and find the u limit that corresponds to it. So if x is 0, okay, that's going to change to 1. If the upper limit of x is 2, put 2 in here, do the calculations, and you're going to get an upper limit of 5. So the correct choice, if we stop right here and leave it at this point, is going to be C. You can integrate without ever having to go back to x if you stay with the u integral. However, you just have to change the limits to u limits. Okay. So at this point, how does this finish as far as integration? Not that that's asked, but let's just kind of see how that works. Some prefer this method because it uncomplicates the integrand. So staying with u, that really is just u to the 1/2. And you can perform the reverse power rule on that. Increase that exponent to 3/2 and multiply by 2/3. And then evaluate with u from 1 to 5. So without ever having to put back in 2x plus 1, you can actually calculate with 5 and 1 into the u here. Sometimes doing it this way uncomplicates the integration process. Sometimes it doesn't help at all. Okay, but it's an easy idea if you think about it, that you have to change the x limits to u limits if you're going to stay with the u integral. All right, so that reviews the FTC. We're going to go next to note card 33 and look at an extension of the FTC.